Calculus Unit 6, Day 53, Part 4 notes. Okay, so now we have a data table here, um, all going up. T-values are going up by 3, and then the velocity gives different values there. Some it's increasing and decreasing, increasing back and forth. So, all right, this table shows values of the velocity v of t in meters per second of a particle moving along the x-axis at selected values of time, t seconds. So what does the value of the integral of v of t dt from 0 to 18 represent? So let's think about that, and if you want to write it down, then we'll check. So the integral of vt dt from 0 to 18 represents the total distance the particle moves from time equals 0 to time equals 18, since the velocity is always positive. So I'm always heading to the right. So we could say it's the net distance, but it's also the total distance. Okay, so now using a left Riemann sum of 6 subintervals, and we notice B we're using left Riemann sum, C we're using right Riemann sum, and D we're using midpoint Riemann sum, although on D we changed the number of subintervals. For all these, we're going from 0 to 18, so indicate the units of measures. So let's set these up, and again, we're doing 6 subintervals, so when I'm going from the left, I'm going to use these values on the left. There's my 6. That's going to be from the left. Now, when I go from the right on C, I'm going to be here. Again, blue is going to be the right. These are the values I'm going to use. And there's 6 of them. Come all the way over here. And then on D, I'm going to do 3 of the middle ones. So what I end up doing is I go from 3 to 6. I'll do it down, excuse me, 0 to 6, but 3 is the middle. And then I go from 6 to 12, 9's the middle, and then I go from 12 to 18, and 15 is the middle. Okay, and so I'll use those values. And in green, that is the midpoint Riemann sum. Okay, so I've pretty much set up B, C, and D, knowing that those are our values, and let's set that up. And again, I know the intervals here for the left and right are from 0 to 3, 3 to 6, so it's going by 3. Okay, so those are the rectangles. So let me set those up. Okay, so let's take a look at these. So on the left Riemann sum, again, I said these are the values I'm going to use to the left. In all my rectangles, and again, let's remember what a Riemann sum means, and it doesn't matter what my function looks like here. If I'm going from A to B, when I'm going from the left, I'm going to draw little rectangles that start with the left value. So some are going to be an overestimation, some are going to be an underestimation. Okay, and I use all those left values right there. When I go from the right, I would go to the right part of the interval and go backwards. So probably if it's a low estimate from the left, a lot of times it's an overestimate from the right, and vice versa. Not always though. So again, so my values are 2.3, 2.7. So I have all these rectangles, but they always have this interval here of 3. That's why it's 3 times 2.3, 3 times 2.7, 3 times 2. Those are the area of all these rectangles, so we just factor that 3 out, and then just add up the x values, or in this case, excuse me, the y values, the values of the function. So we get roughly 33 meters. Then for the right Riemann sum, we start rolling at the m point, which had a value of 2.1. Again, add up all those, multiply by 3, and we get 32.4. And then for the midpoint Riemann sum, we only have 3 subintervals. So when I drew that in there in green, so now from 3 to 9 is 6, 9 to 15 is 6. So those are the 3 values there. Add those up, multiply by 6. Okay, and we get values that are pretty close to each other. And now on part E, hey, use trapezoidal sum of 6 subintervals, again, which is going to be 1/2 the sum of the bases times the height. And again, I know I used the far left interval once, the far right value of the function, and I should say the far left value of the function once, the far right value of the function once. Every other function value of the function I'm going to use 2 times because it's included on the trapezoid on the left and immediately next to it on the right. So let's set this up. And we're 6 subintervals, so I'm going to go by 3. So that's the height. And now Let's write these. Okay, and down the end there, that's plus 2.1 at the end. So 1/2 the height, 3, and then 2.3 plus 2.7 are the sum of the bases, but then it's 2.7 and 2.0. So we just say, hey, there's 2 2 7s, there's 2 2 0s. So we did that on the previous notes, actually the previous two notes. And again, once again, all our estimates were pretty close. Okay, on part F, find, and this is the last one for the notes. So find the average acceleration of the particle from time equals 3 to time equals 9. For what value of t in the table is this average acceleration approximately equal to the derivative? So we know average acceleration is really the secant line of the velocity. And then they're saying, again, for what value of t in the table is this average acceleration approximately equal to the derivative? So let's first find the average acceleration. So let's give myself a little more room here. So I know average acceleration, hey, that's equal to the slope of the secant line. So v of 3 minus v of 9 all over 3 minus 9. Um, Go to the table. V of 3 is 2.7. V of 9 is 1.3. 3 minus 9 is negative 6. So we just found out, hey, our average acceleration is negative 0.233. And again, acceleration is meters per second squared. And then the last thing here is, so the mean value theorem guarantees that a value must exist between t equals 3 and t equals 9 such that the derivative, or the slope of the tangent line, is equal to the slope of the secant line. And in that table, that value is going to be t equals 6. All right, so those are the day 53 notes. Um, and we'll go on to day 54 next class. Make sure you finish up these notes. Thank you.